Hey everybody, I just want to show you guys how to make the graphs required for this current lab. Overall, this current lab is pretty easy. There's hardly any calculations except for the standard milliliters to moles calculation using molarity, but most of the work in this lab is using Excel and graphing things out. So I'm going to be using a previous student's data from a spreadsheet that I have, and I don't really know how it's going to turn out. So if I have any problems, I apologize in advance. So basically right now I have volume and pH inputted into this Excel sheet, and I can just graph it. So using Excel, I could go to Insert, Scatter, and then scatter with smooth lines and markers. And this looks like a pretty decent titration curve. It's basically what you've been seeing all your years of college. I'm going to make a copy of this graph so that I can zoom in to this equivalence point area right here. And so I want to make the graph from volume 18 to about 21 mils. And then I'll just zoom in on the pH as well. So probably 7, maximum 7, with a minimum at 3. Alright, so we can estimate where the equivalence point is, and it's about, I would say, what point is this? 20 to maybe 20.14. In general, like just saying 20.00 is okay, but you don't really know for sure, and it'd be okay for Chem 25, Chem 27 as a freshman and junior or sophomore. But as juniors and seniors, you're expected to be a lot more accurate, especially in this class. So in order to gain accuracy, we're going to take the derivative. And I'm going to make another column of volume. But you're not going to plot pH anymore. You're going to plot the value for the first derivative. So going back to the equations, the first derivative is basically the derivative of pH with respect to the volume. And if you simplify it out, it's basically just the difference between two closely spaced points divided by the difference between two other closely spaced points. And in this case, it's pH and volume. So that's basically what we're going to do. So I'm going to change this header to dpH divided by dV. Alright. So now basically you're just taking the difference between these 2 points and these 2 points. So you can just click at this point. You press the equal sign to make an equation, and then click this minus this divided by this minus this. And because we're calculating the derivative of two different points, of these 2 points specifically, you have to take the average. So the volume would be the average. And you can just type in equals average, and then a menu will pop up. And then you can just drag between the two boxes that have the numbers you want to average. So the cool thing about Excel is that you don't have to do this over again. You can just highlight your values, and if you click on it, you'll see that this box is highlighted. So what you can do is that you look at this box, there's a smaller black box, and you can just drag. And it'll calculate all the different values. So you see how this box moved in respect to the box that you're in. Same for this derivative value. Alright, so I'm going to plot this now. Insert, scatter with smooth lines and markers. And your graph is going to kind of look like this. The reason why this is negative is because this analyte is a base, and you can see because the derivative tells you the slope, so the slopes are going downwards in a negative fashion. So that's why it's like this. I'm going to make another copy so we can zoom in into this first derivative. So the point at which the derivative is the largest is going to be this apex of this graph. So zoom in, probably 17.25, and then 22.84, about. So we get a lot more insight. The apex is going to be around 20.07. And if you compare it with this, you know, the apex, or not the apex, but the equivalence point is from 20 to 20.14. So now we're around ballpark here on this equivalence point. So to get a lot more accurate, we take the second derivative. And what the second derivative does is take the slope between these closely spaced points. And then you'll see that the slopes increase, 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 and at the apex of this point, or of this graph, the slope's gonna top out and be flat, and then go back down and decrease again. So that's what we want to look for. And looking at the equation, the second derivative is this. So it's the difference between the first derivative values divided by volumes. And that's exactly what we're going to do. So I'm going to place these in brackets, divided by the difference in volumes. All right, so I'm going to make the formula this minus this divided by this minus this. Oops. Forgot to put in parentheses. Don't forget your parentheses. There we go. Equals average, because it's the average of two different points. So I get these two values. And I can highlight it again, drag this box down, and there we have our values. Insert a plot, and this is the second derivative. So it doesn't look pretty, but if we zoom in and zoom into this specific area right here, particularly probably 17.25 and 21.25, we can see that there's an inflection point. So I'm going to zoom in a little closer just because you have all this noise here. So I'm going to make this 20, or no, 19.5. How's that? All right. So because there are multiple points where it can top out here, I'm going to estimate the inflection point to be closest to where this is the highest. So I think it's going to be 20, I would say between these 2 points right here. So 20.04 and 20.09. So your equivalence point will be 20.07. And that's about it. It's pretty easy, so don't stress out about it. And if you follow these instructions, you'll be okay in calculating and estimating your equivalence points.